In this lecture, we'll cover Chapter 8 from Charles Galani's book. The chapter is Total Station Instruments and Angle Observations. So I'll start with an excerpt from the book. Calls it Section 8.2, Characteristics of a Total Station Instruments. So what makes a total station a total station? What do they mean by the term total station? So an instrument occupies a point that in our notes we typically call a station. That's typical survey nomenclature from centuries ago. I'm not sure exactly how the term came to be, but a total station is an instrument that has basically everything that you will need to survey a piece of property or conduct a survey. It has three distinct components, which we'll probably come back around on a quiz, and I'll try to differentiate as to when things may also be on FS exams as we go. So the three things are an electronic distance measurement device, an EDM. It's going to be mounted inside the scope. The beam emitter is probably usually right below the eyepiece. An electronic angle measuring component. So the other thing is it can measure angles. So we'll talk about that more in a few minutes. But the third thing is a CPU, or a data processor, not a data collector. But this is an onboard CPU that may be small, may be large, but it's capable of doing computations. Some total stations are I don't know many surveyors that use them, but they basically have onboard data collection so that the CPU will record your measurements as you take them from keyboard commands. Some total stations can also compute coordinates on your forward points and store them, and there are steps on the display that you can go through to retrieve those. So those are the three main things that create a total, or that make an instrument a total station. An EDM measures angles and has a CPU. So they call it computer or microprocessor. I call it a CPU. So these devices can automatically observe horizontal and vertical angles, measure slope distances, all from a single setup, and for the data they can also compute horizontal and vertical distance components instantaneously, elevations and coordinates of points sighted, and display the results on the screen. The book calls it a liquid crystal display. They can also store the data. Most commonly, they transmit the data to an external data collector or controller, as the book calls it now. Older total stations had a cord that you connected to the data collector. This is before tablets really came around, so you may see references to that, and the reference to a communication port is kind of antiquated. I think most total stations probably still have one, possibly as a backup, but every total station and robot that I currently own, and there are several, are Bluetooth connected to the tablet that we run our field software on. And these are the parts of a total station from the operator's perspective, the operator's end of it. And what you'll see is, the vertical axis. I mean, that's really the axis that is that the instrument spins around on. The horizontal axis is the through the middle of it. But talking about the parts, the collimator, I call that a rifle sight or a rough sight. If you're in the lab, you can look through it, and it's kind of like a hologram. It's got a triangle in there, and it points you really close to where the instrument's going to look. If you don't do that, you may just look through the scope with this magnification for a long time trying to find what you're looking for. So the collimator is there to help guide us to get on target, so to speak, quickly. Some of them, or most of them that I know, are those holographic triangles that point you to it. Others are like a rifle sight, two grooves on the back and a post on the front. You'd line those up and you're on it. So the objective focus, the focus for the object, is usually a ring here. The bigger ring that's up against the scope, and the eyepiece focus is right there around the eye. And we talked about parallax and focusing your crosshairs in your object before. One thing that is different, for example, with an auto level to a total station, is there will be a vial level in addition to the bullseye bubble that's going to be mounted on the tri-brac down here. So the leveling head is just the top of the tripod head. This is the display and keyboard, the horizontal motion, which we'll speak about. Well, also I skipped past the handle up here that you can carry it by, and then you have the leveling screws. This is all part of the tri-brac down here, the leveling screws. So then a view, this is of a Leica total station here in figure 8.1. Figure 8.2 is a Topcon. Looks like a GTS 210 or 211D model. I don't think they've made in a few years, but it's still basically the same instrument that Topcon still offers in a total station. A lot of folks have gone to robotic total stations. And the parts are basically the same. You got the handle, this is the collimator or the rifle sight, the object lens, and then this is a vertical lock, and vertical tangent screw, horizontal lock, horizontal tangent screw. So the lock, when you're turning an angle, you're turning when you're observing a point, you're turning a horizontal and a vertical or zenith angle. And we mean zenith angle, but vertical as opposed to horizontal are the more common terms. When you get close, when you get in there, the outer lock, the outer circle, you twist it to the right, and it locks it so that it can't move left to right, except with the tangent screw. The tangent screw, another good term for the tangent screw would be the fine motion screw. That's where you really delicately dial the instrument in to maximize the precision. So, with the circle lock loose, the instrument can spin freely, and then when you get on target with the collimator, you can lock it down, focus, dial in, and then you use your tangent screws to really dial in. This has an optical plumb. A lot of tri-bracs have optical plumbs on them. If your tri-brac has an optical plumb, your instrument will not be able to use an optical plumb. We'll come back to that in just a moment. The optical plumb has a focus for the eyepiece. Most optical plumbs have a object focus back here too, where you focus on your control station, your traverse nail, your iron pin, concrete monument, whatever fixed point in the ground that you're setting up on, and then focus for the eyepiece so that you can eliminate parallax, because it's just as important to get parallax out of your eyepiece as it is out of your object that you're looking through the scope on. And we'll talk about that a little bit more in a minute too. Here's the keyboard, here's the keypad here, where you've got the display, you've got different functions and buttons that can do different things. Now this is the base of the instrument. So this is the base, and then below here, this is the tri-brac. So the tri-brac is everything that the base of the instrument sits down in. The instrument has 3 steel prongs that have notches in them, so that when you turn this knob right here, the tri-brac lock, it locks the instrument into the tri-brac so that it's one integral piece. Now, sometimes if we're using fixed plate prism targets on tripods, we'll use an optical plumb the whole way. The optical plumb is what we'll use to begin with. We'll set a target in it. The total station will be set up on another tripod in another tri-brac, and then you take the tri-brac lock, unlock it, pull the total station out, put the backside prism target in there pointed towards the forward station, carry the instrument ahead, unlock that tri-brac, take the forward prism target out, set the total station in it, lock it in, and then move ahead with the forward tri-brac and target. And then you've got fixed targets that don't move, that are not subject to the wind or to humans not being totally in plumb. The weakness to this is if your optical plummets are out just a little bit, you can pick up some instrumentational error that we will talk about later in this lecture. And obviously below here, the the leveling head is on the top of the tripod, which is sitting down below. So while we're on this, we're talking about the mechanics of a total station. All this up here is the alidade. I call it the scope. The technical term is the alidade, and that's a term that goes back for many years. It goes back into transits and theodolites. It's basically the guts of the instrument, whatever that instrument may be. And the only difference between a late generation theodolite, which are, I guess they're still manufactured, but they're not used much. The only difference between a late generation digital theodolite and a total station is that the total station will have an EDM built in. And I don't know if, I think these are screw holes right here on the front of it, but the EDM more than likely transmits through the eyepiece hole because it's all in there together in the alidade. And you don't hear the term alidade very often anymore, but it is the term that applies to the guts of the instrument. Now, let's talk about how total stations or digital theodolites measure angles. Some of the earlier models had a very finely polished steel plate and a rubber wheel that sat on it. That rubber wheel was like an odometer counter that measured the angles. They figured out though that you got a little grease on that plate and it would, the wheel could slip and you could have huge angular errors, and they never could quite figure out how to resolve that. So what they came up with is a way that the only way to explain it is how the only way that I can explain it is how the book describes it. That is that there's two glass circles. Basically, one is fixed in place that does not move, and one that sits right up above it. There's usually a very thin air gap between them. Sometimes it might be a clear lubricating liquid to make sure that they don't touch, but it's got the angles or the degrees. It's got minutes and seconds, and some of it is inferred. The plates sit on top of each other, and there is a very, very delicate, very precise sensor that sits on top of it, a light and a sensor. And as the instrument, the alidade, rotates around the tribrac and the base of the instrument, these two glass circles change how that light passes between it, and it's programmed so that the instrument can read the changes in the lights and read the plate readings to know what the angle being measured are. And there are two sets of these, one in the horizontal circle, one in the vertical circle. So they give it some terms that I wasn't that familiar with, the rotor being the lower circle and the stator being the upper circle. And so this has a diode that directs collimated light through the circles from below towards a photodetector cell. So in this, there may, it says a modern total station may have as many as 20,000 graduations. So when you think about it, there's 60 seconds in a minute, 60 minutes in a degree, and 60 times 60 times 360 degrees in a circle. There's 1,296,000 seconds of arc in a complete circle. So if there's around 20,000 graduations in these glass circles, that's basically one per minute. So it's able to do some kind of sensing between the minutes to detect and compute and display a very tight 1/60th of a minute into which would be the seconds of arc. When we read degrees, minutes, and seconds, that's where the seconds come from. So figure 8.3 here is a good illustration of a tribrac, and what it is going to do for us is, we talked about the base of the instrument. This is the tribrac itself. here are the lugs that the post on the bottom of the instrument or your target sit into. And here you see an optical plumb. So this is what you would use on the basic tribrach. This would be for an instrument that's not using its own optical plumb, because once you've got one set in here, it uses the same space right here in the middle of the tribrach. So the optical plumb on the instrument is blocked. The way an optical plumb works is you've got the axis of sight that comes in, you have a perfect right angle prism, a mirror that deflects it 90 degrees, so that when your leveling screws are level, then you have a vertical axis line of sight down to the point on the ground. So here 8.4, bubble centering with a 3 screw leveling head. This is something that just takes some practice getting used to if you haven't already. And what I say is, whichever 3 screws you want to look at, the tribrach has 3. You got the line through AB, and then perpendicular to that you have C to perpendicular. And that's also over here where they've got it illustrated as bubble direction. So this is C, it's basically perpendicular to A and B. So as you spin it around, the vial bubble, and these are the graduations, and usually on the instrument it'll tell you this is 20 minutes, this is 10 minutes, whatever this graduation is, which we'll talk about in a few slides, is how far out of level you are. Actual line of sight is that far, and I'm exaggerating. If it's 40 minutes, then from plumb like this over to where you're looking would be 40 minutes. So that also means that that's how far out of kilter or out of adjustment you've made the instrument at that setup. So what you do is you get the vial bubble where it's level in this dimension, but in the plane of A and B. You get it nice and level, and then you turn it 90 degrees so that it's perpendicular to A and B, and then you can adjust just with C. Up here you adjust with A and with B until you get it level. Then you leave A and B alone and you adjust C only. So in theory, when you turn back to A, it should still be level because you didn't mess with the A and B plane. And this way you get the instrument level a lot quicker than you would with a 4-screw setup. But nevertheless, this is the way that you get the instrument finally leveled. Is you get it over two screws, and then you turn it 90 and use the other one to adjust the other side. And that pretty well gets you set up. Again, setting up and leveling an instrument and a tribrach is a skill set that takes a while. This, alternatively, is a view of an electronic leveling system. So if it's one of the total stations that the book speaks about that has the electronic leveling, where it has a concealed bubble with some photo sensors and all, this is what it's going to be reading to you. And we'll talk about the importance of having it leveled and over the point as we get into this. 8.6, very good example. Typically, this is how I'm carrying a total station. On the left, I'm carrying it with my dominant hand. I'm right-handed, so I'd be carrying it by the handle, the dominant hand, and I'd have the tripod over my shoulder. You can tell this is a staged picture because you typically don't collapse the legs and bundle them up and re-strap them in between setups. It just takes too long for no good reason. I'll leave the legs extended just like they were on the last setup and just throw them over my shoulder and go. Another way, in some situations, some topographic areas, is we'll actually put it in the box in between points. And a lot of these instrument boxes have backpack straps, and it's not all that comfortable. It's not padded. It's not like it's made to traverse the Appalachian Trail with, but when you get into some pretty steep, challenging terrain or really thick ground cover where you're having to cut your way through with a machete or step over some things, boxing the instrument and putting the straps over your back frees up your hands. And it's kind of hard to do the same thing with the tripod because that takes up your whole back, but Alternatively, I saw folks. There's usually like a rifle sling. You can kind of see it on this diagram on the left. I believe that's a strap where you can throw a tripod over your shoulder and at least have another hand free. But that's just part of the ways that we can carry a total station from point to point when we're traversing. Traversing being the topic of the next chapter. Figure 8.7. This is a robotic total station. So robotic total stations do the same thing that a total station does, with one key difference. You don't need an instrument operator. It requires a human to set it up, level it, get it over the point, get it rolling, but instead of the operator's eye overcoming parallax and focusing and using tangent screws, the robot has a sensor that it will basically turn to the middle of the glass. Now you'll see that as opposed to our prismatic mirrors, here you can see that a robot has a different kind of glass. It's called a 360 glass or 360 prism, in that it's got those same mirrors set up so that it reflects, but instead of it being basically one-dimensional or one directional is the correct term of your typical prismatic mirror that you'd set on top of your average rod, that's just directing it back directly at you, at the instrument, and you have to make sure that the prism is pointed towards the instrument. A prism, a 360 prism, is able to do that from anywhere. So you don't have to worry about pointing it towards the instrument. This is really important because as they developed robotics, you weren't always able to keep track of exactly where the instrument was and keep it pointed towards it. So that's basically you see here the operator, the technician, has a controller, a data collector. It's probably on a bracket that's mounted to the rod so that he doesn't have to hold it. Everybody has their own preferences there. We like to hold them and be able to walk around. Here you're stuck to the rod. A lot of times we use rod bipods to keep the rod nice and plumb, and then it doesn't need human hands to help hold it up. And then we've got our hands free if we want to do some computing or key in some some commands to the instrument here on the controller. Basically it's speaking to, you see this, they put that crane behind it in an odd spot, but this is a antenna that sticks up above the robot, up above the handle, and they're all a little bit different, but this particular model, which is same as like the newer Geomax, this is an antenna, and there is a radio in the controller that's talking to the robot the whole time. And you tell it through functions on the data collector, find me, turn to the left, you say this is point number 127, you key in your description. If it's a single foresight and go, you tell it that. If you need to plumb it up, probably use your bipod and turn a set of angles. You can do that as well. Robots are great in many ways because that instrument operator is always there as long as the battery's charged. He or she never has to call in sick, take days off, or they don't gripe about working late if you need to finish a job. So the downside is they can lose you. They can lose you behind a building. They can have a hard time tracking you in wooded areas, and that can cause issues and be more time consuming than just having someone on the instrument. But technology has improved, and that's less and less of a problem as robot technology carries along. So moving into section 8.8 and figure 8.8, and this is just to give everybody a little visual. I always would wonder and try to equate just exactly how do I visualize or explain to somebody what an angle is. And we spoke, I guess, in the last lecture about how there is no such thing as an angular distance. That's a misnomer. That's an oxymoron. But you can equate how much distance equates to an angular relationship. And I think this figure 8.8 is pretty cool. Up here at the top, this is the basic math, and you're just taking just a little trig. So you've got an angle. R would be the radius of an arc because the instrument is turning an angle on a circle, so it's like a full arc, and S being the arc length that is subtended, S for subtended. So a 1 minute angular measurement, 1/60th of a degree in 100 feet will be 300ths. So in other words, if you backside a point with 0 degrees, 0 minutes, 0 seconds, and then you turn a full minute so that it goes through 0, 1, 2, 3, 58, 59 seconds, and then it rolls to 1 minute, 0, 0 seconds. You've backsided a point 100 feet away. On that target, on your 100-foot target that you're looking at, the crosshairs have moved 300ths of a foot, which is about 3/8 of an inch. That is a full minute. So a second of arc is a 60th of that 3/8 or 300ths arc that you observed for going from 0 to 1 minute. So at that point, a 300 divided by 60, it's like 5/10,000ths of a foot. So you're getting down into the thousandths of an inch. You're getting into micrometer precision. That's how tight a second of arc is. And you can see other equations that they've done here. At 300 feet, it's 1 inch. There they go using inches. I would call it 800ths of a foot, but so this is probably 0.027 because you're up to 8 when you multiply it times 3. The one on the lower right, which my face cuts off, but is in the figure in the book, I find really interesting, that a 1 second arc at 200 meters, which is over 600 feet away, is only 1 millimeter. So if you had an instrument that could read accurately to 1 second, and you're backsighting a target that's 600 and some odd feet away, and you turn an angle of 1 second, then you're at a millimeter, which is less than a 16th of an inch. It's just very minute, and that's at over 200 yards away. So we do some very precise measuring. Now the way we're going to approach labs is we're not going to try to be super precise. Yes, we're using precise equipment, and we will be very careful, but we will see how easy it is to be doing a tight job as best you can and still have more error than you would have ever thought possible. Definitely not the error that a mathematician would theoretically interject and say, here we are. Because basically, if you got a 4-sided perfect square, 100-foot square, a mathematician is going to say that your last angle, when you set up, you start on 4, then or set on 1, then go to 2, then to 3. When you set on 4, well, when you backsight 3 and turn to 4, the angle is 90 degrees even, and the distance is 100 even. But we know in reality that's not going to be the case because our instruments and our human eyes and our equipment is not without flaw. 8.9 is just an illustration of how we're turning angles. Now the book talks about different approaches to turning angles, doubling angles, direct and reverse angles. They show some redundant sources that are some redundant angular observations that I didn't totally follow. I've never saw before. And they may be very common in other parts of the country, as far as I know, and that's fine. But just understand we're turning angles. So, main thing I point out is this illustration C right here. They call closing the circle or closing the horizon, where when you've got some angles added up to get a check, you would add up, you would turn the outside. So let's just say that X is 40 degrees and Y is 50 degrees. That's 90. So Z should be 270. Now, obviously, you dial that down to the second that was actually observed. But if, say, for example, the sum of angle X, Y, and Z come to 360 degrees, 00 minutes, and 6 seconds, then you would adjust each of your observed angles by adding 2 seconds. And the closing of the horizon, the angle Z there, it confirms that you don't have something blown any worse than 6 seconds in that little example. Now, the reason we're not really expanding on this is, one, there's 3 reasons. One, you don't see a lot of this nomenclature and stuff on the FS exam. It's kind of preliminary, it's kind of elementary, it's below a lot of the level of the SX exam. 2, every surveyor and every survey company does things a little bit differently. So, rather than teach one specific way, like the book does, kind of like with their field note format, which we'll talk about in a minute, I'm just trying to expose you to there are lots of ways to observe angles. There's 360 degrees in a circle. And if you get redundant observations, your most probable true value is the mean of those. So if you double an angle, you talked about the horizontal plate. There used to be, a bottom plate and a top plate, and you could backside was 0. Let's say that you turn an angle of 30. You would leave that angle totally unaltered, loosen the bottom plate, and the instrument's just turning free, and it's still showing you 30 degrees. Well, you would use that lock plate and that tangent screw to get back on your backside with your 30 degree angle. Just say it's 30 degrees, 0 minutes, 00 seconds. Then you would unlock your top motion again, lock it down, dial it in. Let's say you come up with 60 degrees, 00 minutes, 4 seconds. Well, the average of that would be, if you take the total doubled angle and divide it by 2, 30 degrees in 2 seconds. So that's one easy way to say, oh, well, we'll just, it's, once you've turned the angle twice, the true angle is the double of it, or is half of that. That's the average. So that's a little old trick. You've already doubled it, so to take the average, all you do is split it. The more common way is to invert the scope, and that 30, you then just plunge the scope. It'll be looking at it with an inverted scope that's going to give you 210, and then you swing back around with your plunged scope, and you look at your backside, which is going to be 180, and just say that it was that your backside, instead of being 180, was 179, 59, 54. Well, then that's 6 seconds difference. So you actually turned a 60, you actually turned a 30, 0006 your second time, so your average would be 30 degrees, 00 minutes, 3 seconds. So there are lots of different ways of doing that, and a lot of what you'll do in the surveying world, if you pursue a career in this, is going to be according to how the surveyor wants it done and according to how the software operates, because some software does direct and reverse sets really easily, but they get really blown out of the water when you just try to do a traditional double. Another weakness with the traditional double angle is if you have any kind of collimation error inside your instrument or any kind of centering error in your instrument, you're not compensating for it. You're just taking 2 redundant direct observations. If your instrument has any kind of error in it, which they all do, some of it is fairly non-detectable, some of it is, when you take a reversed scope, then you're accounting for that. So your average is probably pretty good. It's just like with trig leveling, you take a direct and reverse on a foresight, because any instrumentational error is going to typically average out. If your direct is measuring a little bit low, then your reverse is probably measuring it equally high. And so the reverse, or the average of them, is probably just dead on the money, or it's very close to dead on the money. Again, here with this slide, I'm just going to say again, field notes for measuring horizontal angles will vary. Everybody has their own way. We'll use the format that I find to be the most common in Georgia and places that I've worked, and we will just go with that. Basically, any format that is legible that you can use and that other people can look at and understand what you did is adequate. And this is this is in the 21st century. We're not taking field notes unless the data collector or the tablet has died, or we can't afford one yet. And it's just kind of a small scale, going out and locating some stuff for an engineering project or for some construction layouts. So that's another reason we're not really dwelling on all these note formats, is none of that's on the exam. It's all individual taste, and most all your field notes after this class and after surveying 2 are going to be with a tablet or a controller, data collector, etc. So I just wanted to mention that. Here, 8.13. Here's different ways to measure deflection angles. The book describes it fine, but here you can see that the deflection angle from F backside E to G is 12, 15, 10. That just basically means it's 192, 15, 10 is your angle right, because you're just taking this 180 degrees out of it. And of course I did draw that wrong. It's more like this. It's more like, this is the 180, and then you got the 12, 15, 10. And then, if you want us to look at the whole angle right, it's 192, 15, 10. And then you can deflect to the left. The thing with the deflection angle is you have to know if you're deflecting to the right or to the left. And everything in stations, everything with routes, which deflection angles are, it's starting at the 0 point and looking down station. So if you're looking down the road as you go, to the right is to the right, to the left is to the left. Some of the equipment that's involved in total station, we talked about earlier, if you've got these target plates that sit in a tri-brac, I've just circled it. These bases right here have the same 3 lugs that lock into the tri-brac down here. It even has a collimator up here. Sure does, where you can point that right at the instrument so that you have a nice directly pointed prism and target plate. Notice that this has, nice point here that's horizontal that you would turn to for your vertical angle, and a nice one here for your vertical angle. This also works with instruments that do not have optical plumbs. Let's talk about that for a minute. This target setup here has an optical plumb. That's what it is right there, looking in the side, so that when you pull this out, there's nothing in the way. The instrument's optical plumb can sit right on top of it. So it's got that 90-degree mirror that puts you right over the point, just like we were talking about. However, we're just talking about this because it's simple and it's a good place to start. In modern practice, most instruments have laser plummets, and the laser plummet, in my opinion, is far superior to the optical plummet in daily operation. Now, it might not be if you're doing really high level geodetic work at night, but for boundary and topographic surveying in the southeast, including high dollar ALTA surveys, the laser plummet is superior to the optical plummet. So if you were doing a leapfrog traverse operation and your instrument has a laser plummet, then you would use this optical plummet on your forward tri-brac to get the prism over the point. But again, you got to be careful. I have done leapfrog traversing and moved ahead and used the instrument's optical plumb or laser plumb and found the tri-brac to be off a little bit. And the more it's off, the worse it is. And if it's off more than about a half a hundredth, hundredth being close to an eighth of an inch, so like a 16th of an inch, if you're off the point that much when you slap the instrument on it, you're introducing some angular error that you're going to have to fix. Now, the book talks about some adjustments and calibration and things to work with and things to do to adjust the instrument. I'm going to say this. I'm not going to cover it. I don't do it. It's kind of like working on your own car. If you've got the know-how, you got the tools, you know what you're doing, and you're comfortable, if you break it, it's yours, then go for it. I have a friend and staff member here at my firm that loves to do that, and he's great at it, but he doesn't do major repairs. He just does minor adjustments and calibration to make sure that everything's in. So, that's the first topic of this slide. Second is section 8.18. talks about trigonometric leveling, or total stations for determining elevation differences, which is just another way of saying trigonometric leveling. And we've already covered that in the other lab, so we're not going to really go into that, and I just kind of left a bookmark. Typically what we do when we survey is we run a random traverse. Now, I don't know that I'm really big on X and Y and what they're doing here, but this is, if we're surveying through a wooded area, we need a clear line of sight between the targets. And obviously, if we're trying to run trying to figure out where the line is between X and Y, it's looking like, I'm hoping that's a straight line. It looks a little curved, but we might set up on one and maybe backside X and put an intermediate point over here on A. This is all just done with coordinate geometry and just trigonometry, and you get out here. So the instrument is set up, for example, just make it simple. The instrument is set up on 1 and 2 and 3, but what we're interested in over here is X, A, B, and Y. So we took the path of least resistance with our equipment and our carrying the equipment through the woods and our line of sights and trying to cut fewer limbs out of the way with machetes and bush axes, and just came on ahead. 8.22 is a graph, which I like, of sight distance versus angular accuracy, and it's kind of funny they felt the need to put it in a chart, but let's just put it in perspective. The further out you get, the more angular accuracy you can have, because a second of arc becomes a bigger part of your target. We're talking about how much that angular measurement makes. The further out you get, it makes a whole millimeter in a 200-meter sight. So you can read theoretically a meter, a second of arc pretty well. You can discern a millimeter's width. It's like a crosshair at 200 meters. But at 20 feet away, that same millimeter might be a minute and a half. So what this is basically saying is the further out you get, the closer you approach being able to dial your angular accuracy down near zero, and the closer you get, you're struggling. The way I infer it here is they're saying at 100 meters, that's 300 feet. According to this graph, when you get down to like 50 meters, it's like 150 feet. They're saying that 4 seconds is about as accurate as you can turn with the eye. And I agree with that. It's probably about the same for a robot, but that's, you can do the math and see how much actual arc length a 4-second arc makes at 150 feet. That's not going to be much. 8.23 in the book, they're going into, or actually figure 8.23, they're going into some trigonometric leveling notes. Again, it's just everybody's format. We're just here to teach the theory, not note keeping. You're not going to be note keeping more than likely in the real world. Somewhat out of order, figure 8.24, these are the reference axes. So you got the horizontal axes running through the middle of the instrument, and then running around like this, you've got the vertical axis. The plate bubble. Now here's what we're going to talk about a little bit. If your bubble is out of alignment, it doesn't just mean that the instrument's not level. It means that your laser plummet or your line of sight for your optical plummet is not truly plumb. So let's just say this is a vertical line right here. And that's where it is, figure 8.25 in the book. And however much out of level you are, which, especially a vial bubble on the side of an instrument, not your bullseye bubble, but a vial instrument on the side, it's going to have some graduations on it that tells you how much actual rotation of the instrument head each one of those graduations on the bubble makes. And so if you're out 15 minutes here, because we're not talking about looking at an angle out there, we're talking about how much out of level the level head is, or the tribrac is. 20 minutes is nothing in a few inches across the base of an instrument. You can't see it with the naked eye. You have to try really hard to find it with an instrument. Well, that's how far off center you're pointing. So if you're 20 minutes off, angle alpha here is 20 minutes. Then that's how you're looking 20 minutes off down through your scope. And it might be not too hard to get into several minutes. You might not get all the way up to a degree until your instrument detects that it's that much out of air. Maybe it has an auto compensator or has some kind of sensor that says, wait a minute, you're out. But that's what happens. That's why it's so important to get the thing level and get it over the point and to keep it in adjustment. Here's a geometry of your instrument being disleveled. So basically, your instrument is here. Don't know that I can think of a little bit better way to illustrate this, but S is your forward point. It's basically saying that whatever that alpha angle is, your instrument is going to be out that much. Now I'm exaggerating with my hands, but you're going to be out that much. However much your instrument is out of adjustment, that is how much air you're throwing in the position of your forward point. So you think it's actually here at P, but it's really over here at P prime, or reverse. So I would probably look at it, well, their next illustration is pretty good, 8.27. This is showing you if your point is actually right here inside the middle of the circle. Let's just say that the 0 is where the instrument is set up, and alpha is the angle that you turn. You back-sighted point 1, and you've turned an angle of foresight to point 2. So you measured an angle of alpha. But now, what if your instrument is out of plumb, and I'm going to switch over to blue. Let's say that your nail, concrete monument, rebar, whatever, is actually over here. Then you've not measured, but let's say that the blue circle is where your nail is. Let's say it's a traverse nail. But the red circle is where the instrument's set up because it's not level. It's not over the point well. Either you forgot to adjust it when you set it up and slide it over to where it was supposed to be, or you have some bubble error. You're not level. So because you're not level enough, you're off that much. And you could easily be 2 or 3 hundredths off the point. Then you've got some angular error in your forward point. Your error for point 2 is going to be this, and your error for point 1 is going to be this. And this is exaggerated a little bit for illustration, but notice that error of 2 is less than the error of 1. And that means that whatever the difference is between those two, that's how bad out your angle is. Here's something else to think about. Let me erase this. Notice, well, let me erase the P2. Let's put a dimension line on here. Obviously, this line the blue line is longer than the red line. So you measured the red line because the instrument is set up in the circle, but it's not over the point. So, looking like it, the point to P1 is probably not off an appreciable amount, but the distance between the point and P2 is probably going to be off. In this illustration, say it's 2 or 3 hundredths. I've seen that. It's not uncommon. That's if you're just off the level and over to one side. There are basically, they say one of 3. There are 3 different scenarios. The second one is you're out in front of it. Let's say that you're out of level through the instrument closer to the points. Well, now you don't even have any compensating error. The error 1 and error 2 are both compounded into the error of your setup. So it's really alpha plus E1 plus E2, but you have no idea what E1 and E2 are because you don't realize that you're set up off the point. This is where some of our angular error will accumulate in the course of a traverse. And here, just say that the point is set up back here behind the point. So you're measuring a distance that's longer to both, whereas in slide 2, you're measuring a distance that's shorter than reality. Here in slide 3's scenario, where the point is back behind point 1 and point 2, you're measuring distances that are longer, but you're also turning an angle that is smaller, because you've got alpha that you've measured. But in theory, error 1 and error 2 come off of that. So you're measuring an angle that's too big, or that's too small. It needs to be bigger if you were scooted up on top of it. So some of the latter parts of the chapter, it's good that you read it. Don't worry about it too much. Some things to remember at 8.22. You're sighting on, setting up, or over the wrong point. That basically just means that you're not directly set up on the point. Calling out or recording an incorrect value. You might do that in a lab or in some instance where you're using a field book, but a data collector eliminates that. Improper focusing of the eyepiece and introduction of parallax error, that's number 3, that can happen. And leaning on a tripod or touching it, it's very natural. I see students, just conducted another lab this afternoon, and students invariably they're putting their hand on the tripod to help steady themselves, or because it just feels natural. But we're talking about micrometer readings, and you move the instrument, or the instrument's out of air just a few seconds or a few minutes of arc, that transfers down the field towards what you're looking at. When you touch that instrument, you're moving it. I would even challenge you, if you don't believe me, look at a sight out there without touching the instrument, which is the proper way. Don't be touching the tripod, touch the instrument, and then once you've got it, take your hands off the instrument, look at the eyepiece, and then just bump the tripod very easily. You'll see how much error that introduces. Thank you very much. We'll hit chapter 9 next and start learning how to traverse. Thank you.